Okay, next video in forces, number 3. This is for your physics paper 2, and it's on deformation and elasticity. Deformation, firstly, is the scientific term for when you change the shape of an object. So look here. Here is the original object, and you can change the shape in 3 ways. You can stretch the object, make it longer. You can bend the object, or you can compress the object, make it kind of squashed. Deformation is just the term we use for when you change the shape of an object. All these objects have been deformed. Now, in order to cause any deformation, you need to apply 2 forces on this object. Just think about it. If I apply only 1 force, say on this box, this way, all it's going to do is accelerate, not move, accelerate towards the right. So in order to, say for example, compress the object, I'm going to have to apply 2 forces, okay? And that's really important you get it around, that 2 forces are needed to deform objects, okay, which is shown here. 1 force is called a resultant force, and that will accelerate the object. Going back to deformation, there's 2 forms of deformation. There's elastic and inelastic. You should be pretty familiar with this. An elastic deformation is when an object returns back to its original shape when the original forces are removed. For example, an elastic band. So if you go back to our original here, if I press on this object, and then when I let go, it returns back to usual, a bit like a sponge, for example, we can say that's an elastic object. Same with a rubber band, an elastic band. You know, when you stretch an elastic band and you let go, unless you've fractured it, you've broken it, okay, it will go back to being a rubber band, its original shape. Whereas inelastic deformation is an object that does not return back to original shape when the forces are removed. And the best example of that in my mind is Play-Doh. So when you play with Play-Doh, when you press down on the Play-Doh and you deform it, it doesn't return back to what it was before you deformed it. Okay. Now, a lot of this this module and the required practical is all about forces on a spring. So have a look here. We're not going to go through the required practical, that will be just before the exam. But the required practical is basically you get a spring and you hang some masses off it and you see how much it extends and you plot a graph to show and find the spring constant. We're not going to go through that now, but we're kind of going to go through the calculations involved. So here we've got a spring, and that spring has an original length of 20 centimetres. On the right here, on that same spring, I've attached a mass. There is a force being exerted on the spring downwards, and that's causing the length to extend. So the length of the spring has gone to 30 centimetres. So the extension is going to be 30 minus 20, which means it's 10 centimetres. Now a top tip, guys, is make sure you convert centimetres back into metres. Convert into metres for extension, please. And the way you convert centimetres into metres is dividing by 100. So you can see here, although the extension, you're right, it is 10 centimetres, the extension in metres is divide that by 100. 10 divided by 100 is 0.1 metres. Now we can do 2 different calculations based on the information that we've got up here. We can first of all do what's in pink here, which is the force on the spring is equal to the spring constant times the extension. This is one you need to remember for your exam. F equals K times E. You're going to put it into a triangle. F would be at the top, K and E would be at the bottom. So look, here we've got a spring that has a spring constant of 15 newtons per metre, and it extends by 10 centimetres like the spring above. Calculate the force applied to the spring. So here we go, F equals K times E. My K is 15, my E extension is 10 centimetres, which is 0.1 metres because I have to divide by 100. So F equals KE, which is going to be 15 times 0.1. Do it in your calculator, and the force applied to the spring is going to be 1.5 newtons. Now an extra added bit that they can ask you about is, okay, well based on the force that you've just calculated, what mass was actually added? Well, you know that weight equals mass times gravity. So weight is a force, so rearranging that using an equation triangle, weight at the top, mass and gravity at the bottom. So cover up mass, mass is weight divided by gravity, as we can see here, mass is weight divided by gravity, which is 1.5 divided by 9.8, and in your calculator you can see that it's 0.15 kilograms, 150 grams has been added. What else could you be asked about? You could also be asked to calculate the elastic potential energy in the spring, stored in the spring when you extend it. Key fact, guys, is that you only store energy in a spring or an elastic object when it's either stretched or compressed. When there's no forces acting on it, there's no energy stored in that object. This is one that's given to you, so please do not, there's no need to memorize this. This is in the equation sheet, but remember you may need to use it. So for this spring here, the elastic potential energy, we know the spring constant is 15, and we know the extension is 0.1. So we need to do 0.5 times the spring constant times the extension squared. which is going to be 0.5 times 15 times 0.1 squared. You plug all that in your calculator, and this is exactly what appears: 7.5 times 10 to the minus 3 joules. You can write that down in the exam like that, or you can convert it into decimal form, which is 0.0075 joules.